Now we're going to do something called logarithmic differentiation. And doing this is going to involve taking the natural log of both sides of an equation in order to take a derivative of functions that we don't know how to differentiate already. Let's remind ourselves of all the properties of logs before we get started because we'll need these. So if I have the natural log of a product, then I can break this up into two natural logs. So the natural log of A plus B, so a product inside of a natural log gets separated as addition outside. Division gets separated as subtraction of two logs. And then if I have ln of A to a exponent, I can bring the exponent out front, making this k ln of A. Okay, so if we look at this first example, y equals x to the sine of x, this is not an expression that we know how to differentiate already. And the reason why is because there's an x, there's a variable in both the base and in the exponent. And the things that we've dealt with so far, we've been able to deal with things like a number to an exponent, 8 to the x. We know that its derivative is 8 to the x ln of 8. Or we know how to deal with using the power rule, things like x to a number. This is just the power rule. But what we don't know how to deal with is a thing where both the base and the exponent have functions in them, and neither of these is just a number. So the way that we're going to deal with this is we need to get the variable out of the exponent here. So what we're going to do is we're going to do something called logarithmic differentiation. What that's going to mean is that before we take a derivative, we're going to take the natural log of both sides of the equation so that we can simplify that exponent. So to do logarithmic differentiation, we start out by taking the natural log of both sides of our equation. So we have ln of y is ln of x to the sine of x. Then we use the properties of logs to simplify this side of the equation. In this case, the only simplification we can do is one of this form where we're going to bring the exponent down. So we're going to bring the sine x out front. So all I'm doing so far is just rewriting this expression. I have not taken a derivative yet. Okay. So when I take the sine down, I get sine of x times ln of x. And now I'm going to differentiate both sides of the equation. And when I differentiate both sides of the equation now, I'm using implicit differentiation because we have the y inside of the function, inside of the natural log. Okay? So when I take the derivative of the natural log of y, remember y is a function of x. So when I take the derivative of natural log of y, I get 1 over y, but then I have to multiply that by y prime because of implicit differentiation. Remember, implicit differentiation says every time I take the derivative of something with a y in it, I take its derivative like I normally would, 1 over y, but then I have to multiply by the derivative of y, okay? And then on the other side, I only have x's, so I just have to take this derivative like normal. Here I have sine x times ln of x, so that's a product rule. The derivative of sine of x is cosine of x. We leave the ln of x alone. Then we leave the sine x alone. We take the derivative of ln, which is 1 over x. Okay, so after we've differentiated both sides of the equation using implicit differentiation, now we want to solve for y prime. So to solve for y prime, I can multiply both sides by y to get rid of the y there. So I get y prime is y times all of this. And then there's one last step here. We don't need a y in our final answer because my original expression was y is equal to something. So I'm going to replace y with the x sine of x because that's what y was equal to originally. That way my derivative is just in terms of x instead of having an extra y in there. So y prime is x to the sine of x. And then the worst part about these problems is copying everything down again. Okay, and so that's what we get there. So with implicit differentiation, we take the natural log of both sides first and then simplify. The hope is that when we simplify, we're going to get something that we can differentiate. And then we use implicit differentiation to take the derivative of both sides of our equation, and then we solve for y prime at the end. So let's use the logarithmic differentiation for this one. So this is a problem that does not require logarithmic differentiation. The last problem required logarithmic differentiation because we didn't have any other ways to solve that problem. This problem I could do a quotient rule and two chain rules to solve this one. So this problem we could solve without logarithmic differentiation. But let me show you how logarithmic differentiation will make this problem nicer. So we're going to get started by taking the natural log of both sides. So I'm going to have ln of y is ln of 2x plus 1 to the 8th over the square root of x squared plus 2. Now we want to use properties of logs to simplify the right-hand side of the equation. So we can use the fact that division inside of a log turns into subtraction to make this ln of 2x plus 1 to the 8th minus ln of the square root. I'm going to rewrite the square root with an exponent. The square root of x squared plus 2 is the same thing as that expression to the 1/2. That'll just allow us to simplify this piece more. Okay, and now I can bring the exponents down. So I can make this ln of y is 8 ln of 2x plus 1 minus 1/2 ln of x squared plus 2. And now this is as far as I can simplify this expression because now I'm left with addition inside of my natural logs. None of our properties tell us what happens when there's addition inside of the natural log, so I can't simplify these anymore. I can't bring this 2 down because it has that addition between the other piece. It's not this whole expression being squared. So this is as much as I can simplify. Now I'm going to take a derivative. Okay, so as soon as I've simplified as much as possible, I'm going to differentiate. The derivative of ln to the y is still going to be 1 over y, coming from, that's what the normal derivative of ln of y would be. But then because y is a function of x, using implicit differentiation, we get that y prime. Okay, so to take the derivative of this piece, the 8's a constant out front, so it can stay out front. Then we use the chain rule on the natural log piece. The outside function is ln of x. The inside function is 2x plus 1. The derivative of ln of x is 1 over x. The derivative of 2x plus 1 is 2. So we put the 2x plus 1 inside the 1 over x. So I get 1 over 2x plus 1. And we multiply that whole thing by the derivative of the inside. Multiply that by the 2. Okay. And then to take the derivative of this piece, the negative 1/2, again, is a constant. It stays out front. And then to take the derivative of this, I'm going to use the chain rule again. The outside function is ln of x. Its derivative is still 1 over x. The inside function is x squared minus 2. Its derivative is 2x. So I'm going to put the x squared minus 2 inside the derivative of the outside function. And then I'm going to multiply everything by the derivative of the inside. Okay. I'm going to simplify this just a tiny bit. I noticed that the 1/2 and the 2 will cancel each other out. The 2 times the 8 will give me a 16. So I can write this as 16 over 2x plus 1. That doesn't simplify any further. And then this x I'll put up top. So I can write x over x squared minus 2. If you didn't simplify that at all, that would be okay. And then I'm going to multiply the y over on that side. So I get y prime is equal to that whole expression. And then remember my last step is I need to replace y by the original expression, which is pretty messy in this case. So 2x plus 1 to the 8th over the square root of x squared plus 2. And then all of that times this expression. 16 over 2x plus 1 minus x over x squared minus 2. Okay. So I think that logarithmic differentiation is a little bit easier here. If you preferred to just use the quotient rule and two chain rules on the original function, that would work as well. So multiple ways to solve the same problem. The final answers look a little different. Really, they're the same thing, just reformatted. So if you tried to check it with the quotient rule, your answer will not look exactly the same as this, but they should simplify to the same thing.